All right, here is a quick video to run through the calculations for Laboratory 8, which is on the combustion of steel wool. For the most part, the experiment's pretty self-explanatory, but I want to step through each of the calculations so we can talk about them and see if you're having some problems. Hopefully this will help you kind of step through it. Okay, let's go to the next slide. So the data we're collecting for this particular lab is really only two things. We're doing multiple trials of it, but we're only collecting two pieces of data in each trial. One is the mass of the steel wool before we burn it, and the second piece of information is the mass of the steel wool after it burns. All right, so we're calling the first one M reactant and the second one M product. All right, so on your table, that's where you're getting the measurements from the pictures of the scales, right? So I took the picture of the balance at each time, and so you can, list them all out. So beginning and ending of run, before and after I combust them. So that gives you your data to work with. So after you've got your data, how do you do your calculations? Well, the first step of the calculation is you need to know how many moles, because this is a stoichiometric calculation, so you got to work in moles. So you need to know how many moles of iron you had originally. We can assume the entire steel wool is iron. It's what's called mild steel, which is mainly iron. There's very little contaminant. There's very little other things in it. Steel is mainly iron and carbon alloyed together with trace minerals. Mild steel has very little carbon in it and even less trace materials. So for all intents and purposes, steel wool is what we would call cast iron. So it's not really anything other than iron. So to do this, it would be a straightforward molar mass calculation. So you have to figure out the molar mass of iron, which you get from your periodic table, and then you have your mass of your reactant, and then it's a straight grams to moles calculation like we've done throughout the rest of the course, right? So you're going to take your mass, you're going to divide it by the molar mass of iron. So that gets us what we call mole sub Fe, or mole sub iron, how many moles of iron I started with. The second thing I need to do is I need to figure out the mass difference between the beginning and the end of the experiment. So what we're figuring out here is how much mass was gained by the steel wool during the experiment. So if you looked at the experiment and you watched the video, you notice that when the steel wool combusted, it actually went up in mass, right? So it went up in mass, which means that we gained mass during the system. So to figure out this mass difference, all we do is take the mass of the product, so the mass at the end, and subtract the mass of the reactant, the mass at the beginning. So this is going to give us our difference in mass in grams. Okay, now that mass that we added to the system is oxygen that we combusted into the iron. Because what happened was when we lit the iron on fire with the battery, the iron combusted with the oxygen in the air to form some type of iron oxide, right? Rust, essentially, a type of rust. And so the oxygen becomes bound into the iron. So any mass that's added into the system, because the iron didn't disappear into the atmosphere, it's still there in the steel wool. Any mass that entered into the system is oxygen that we put into the system, right? That we bound into the iron. So that mass difference is our amount of oxygen. Well, just like we did in calculation 1, we know the grams of oxygen we added, that's the mass difference. We know the molar mass of oxygen, and again, we're just going to use oxygen as an element, so 16 grams per mole. And between those two, it's a simple molar mass calculation. Our mass divided by 16 gives us how many moles of oxygen we have. So now we know the moles of oxygen and the moles of iron. Now we need to see what ratio are they to each other. Okay. What we're trying to figure out is what's called an empirical formula. Now, an empirical formula, as it states here, is the lowest whole number ratio. All right. So to get the lowest whole number ratio, the easiest thing you can do is take one and divide it by the other. Okay. Now, traditionally, you do it as you take the larger one and divide it by the smaller one. It works either way. This is a pretty simple one, so we can do it anyway. But if you want the simplest calculation, the easiest way to do it is take the larger of the two values and divide it by the smaller of the two values. But we're just going to do it one way. We're going to take the moles of iron and divide it by the moles of oxygen. All right? So when I take the moles of iron that I calculated in step 1 and the moles of oxygen that I calculated in step 3, and I divide iron by oxygen, my number that I get out of that, my division, right? The number I get out of that division is the amount of iron, the moles of iron per 1 mole of oxygen, all right? Or the number of iron atoms per 1 oxygen atom. Now that's going to come up with 3 possible scenarios, okay? And you're going to see which of these scenarios that I list in a second most fits the data you have, all right? So there's 3 possible scenarios I can get. The easiest one is when I do that calculation, it equals 1, or close to it. It won't be exactly 1, okay? None of these are going to be exact values. They're going to be close to them. So if you do the calculation and the value is, 0.95, you're not like, oh my gosh, it's off. That's 1, right? So if your value is close to 1, and that's what you're really choosing, is it close to 1, 2, or 0.5. So if your value is close to 1, then that means your empirical ratio is 1 to 1. So that means for every oxygen, there is 1 iron. So your empirical formula would be FeO, right? So it would be iron 2 oxide. Because remember, oxygen's got a 2 charge, so if it's a 1 to 1 ratio, the iron's got to have a 2 charge, right? Now, same ratio is 2 to 1. So that means my calculation that I did in the previous step would be 2. If that means I have 2 irons for every oxygen. So my ratio would be, my empirical formula, would be Fe2O. Now that would mean if it was Fe2O that I would have iron 1 oxide, because each iron would be a +1, the oxygen would mean a -2. All right. Now the next one we could get is we could have a ratio, and I have no idea why I wrote that as ration. Sorry about that. Or ration. I guess it'd be ration, wouldn't it? Yeah. Ratio is around 1 to 2. So that means when I did my calculation, I got a calculation of somewhere close to 0.5. Now what that means is I have 1 iron for every 2 oxygen. All right, so that's a little different. Last I talked about how much iron I had for 1 oxygen, but since my number is less than 1, and significantly, again, if you get like 0.8, consider that to be 1. Likewise, if you got 1.8, I'd consider that to be 2. Okay, so kind of round it to the closest one of these 3 you get. So if I got 0.5, that would mean for every 1 iron, I actually had 2 oxygens, which would mean my empirical formula would have to be FeO2. Now that would be iron 4 oxide, because now I got 2 oxygens, each of them -2. So 2 times -2 is -4, and I've got 1 iron to counterbalance that. So I would have iron 4 oxide. So you're going to have one of these 3 outcomes. Okay, so your number is going to either be close to 1, 2, or 0.5. All right, choose the best one that matches your data and use that for your final answer. All right, and then name it appropriately. It's a pretty straightforward set of calculations. All you've really got to do are 2 molar mass calculations, and then a subtraction and a division. That's it. And then you can and you'll get everything you need done. So I'm going to go ahead and post this, and you guys can ask me any questions. If you're in my morning class, you can ask me questions in the morning. If you're in the afternoon class, Dr. Bagkey can give you some ideas from there. Okie dokie. Talk to you guys later.